Hello everyone, we are presenting a comparison study of nonlinear optimization of step durations and foot placements for dynamic walking. In order to deal with disturbances such as pushes, three common strategies are used. These are the ankle strategy, where the center of pressure is manipulated, the hip strategy, where changing the angular momentum around the center of mass is used to deal with external disturbances, and the stepping strategy, where a step is taken in order to reduce the acceleration of the center of mass. While ankle and hip strategies are used for smaller disturbances, we humans tend to take a step or even a few steps of different step length for larger disturbances. The same holds for robots. In our comparison study, we will study the stepping strategy and analyze when, where, and how long to step for maximal disturbance rejection. In our paper, we proposed a holistic and a sequential optimization approach to obtain three walking parameters, which will determine the ability to recover from pushes. These parameters are the remaining duration of the current step, the step duration of the next step, and the location of the next step. In the holistic principled approach, we simultaneously optimize the remaining current step duration and the next step duration and location to achieve stable walking. The optimization problem considers the robot kinematic constraints by defining minimal and maximal admissible step durations and length as inequality constraints of the optimization problem. We use the results obtained from this approach as a baseline. For a sequential approach, we propose to separate the holistic three-parameter optimization problem into two one-parameter optimization problems. By doing so, we're able to reduce the computational time drastically. In the first stage, we determine the optimal remaining step duration t is 0, and the resulting states from stage 1 are used as initial condition for the next stage. We then analytically express the step location p as a function of the next step duration t is 1. In stage 2, we can then minimize the next step duration t is 1 by using the previously obtained walking parameters t is 0 and p. In a final simulation, we perform multiple pushes from the front and back. We assume that the walking dynamics of the robot will behave like a linear inverted pendulum. At 3 seconds, an external push is active for 300 milliseconds. As a consequence, the robot takes a step backward in order to deal with the backward push. Here we can see that the robot takes a step back to resist the backward push. It takes a large step forward when it gets pushed forward. The simulation shows that the holistic and sequential approach yield the same results for all three walking parameters. Despite having the same solutions, the computational time is different for both approaches. Due to solving two one-parametric optimization problems, the computational speed of the proposed sequential approach is roughly 30 times faster than the holistic approach. If you're interested in this topic and want to know more about the details of the paper, for example how and when the holistic and sequential approach differ, please visit our poster during the interactive session. Thank you for your attention.